Find the equation of the normal line to the curve f at x equals x plus 2 over x at the point 1, 3. So we're going to talk more about normal lines and tangent lines when we look at vectors, but you do have the diagram there to refer to. So the normal line is just a line that is perpendicular to the tangent line. So what we're going to do first of all is we're going to figure out what is the slope of the tangent line, and we can find that by finding the derivative of my function. So the derivative of the function, I might want to rewrite this function first as x plus 2 x to the negative 1, and then find the derivative of the function, which is going to be 1 plus 2 times negative 1 x to the negative 2. And I'm just going to clean this up, so it's 1 minus 2 x to the negative 2, or 1 minus 2 over x squared. So this is the slope of the tangent line. So what is the slope of the tangent line at the point 1, 3? So now we're going to work that out. So the slope of the tangent line at the point 1, 3 is going to be the derivative at the point 1. So f prime at 1. So I'm going to substitute in 1 where I see my x's. So this is 1 over 2 over 1, or just 1 minus 2, which is negative 1. So if this is the slope of the tangent line, then the slope of the normal line is going to be the negative reciprocal of this. So it's going to be the negative of, right, my negative 1 over negative 1. So 1 over negative 1 is really just negative 1. And so this is going to be positive 1. So the slope of my normal line is 1. And I still want to think about what is it at that point 1, 3. So once I figure that out, I'm going to use point slope formula to come up with the equation of the line. So y minus y1, which is 3, is equal to m, so 1, times x minus x1, so x minus 1. And I'm just going to solve that. So y is equal to x minus 1 plus 3, or y is equal to x plus 2. So this is the equation of the normal line to the curve at the point 1, 3. Example number 9. Analyze the differentiability of each function. So we're going to start with y equals the cubed root of x. If it's helpful for you, you can sketch a little diagram of what the function is going to look like. And you could either sketch it if you know how to sketch it by hand, or you can use Desmos to refer to what the graph is going to look like. So I'm just going to go ahead and draw a diagram here. So the cubed root of x is going to have a point at 0, and it's going to be 1, 1, and it's going to be negative 1, negative 1. So it's going to look something like this. Okay. So this is the graph y equals the cubed root of x. And so what we can see is that our function is continuous. There's no breaks in my function. I can start from one side and go to the other side without taking my pencil off the paper. So it's continuous, which is great. So I know it's, that's good. But I also need to think about where might it not be differentiable. And we've talked about some different ways to identify differentiability from the graph. So we can see from this graph that it's not going to be differentiable at 0, because if I was to draw the tangent line through here, it's going to be vertical. And so the slope of a vertical line is undefined, so it's going to have that infinite slope there. And because it's going to have infinite slope there, we know it's not going to be differentiable. right? So that's important for us to think about. So this is an infinite slope. So we know it's not going to be differentiable right from the graph. But what if you didn't want to graph it? What if you didn't have a graph to think about? Well, we can analyze the differentiability by looking at the derivative of the function. So the derivative, I first might want to write this as something that it's easier for me to find the derivative of. So f at x is equal to x to the 1/3. And so the derivative of this function is going to equal 1/3 times x to the negative 2/3, which is the same as writing 1 over 3 x to the 2/3. But I can also write this as a radical, which is going to be 1 over 3, the cubed root of x squared. Now, it's easy to see from this rational expression that we're going to have some restrictions. We can't have our value to be 0 because the cubed root of 0 is going to be 0. And then if we multiply that by 3, it's also going to be 0. So the denominator is going to be 0. So we can't have x can't be 0 because it'll make the denominator 0. So we know that it's not going to be differentiable at this point because that's going to be where we're not going to be able to find the derivative of that point. So this is where it's not differentiable. And so that's how we find it algebraically, or we can also take a look at what the graph is going to be. And we can see from the graph that the point is actually 0, 0. So if I wanted to find, the y value, I could go ahead and figure that out. Not an issue at all. Okay. Let's take a look at example B. Here we have a function x equals 2/3. And so again, this might be something that you might want to refer to a graph for, or you can just take a look at the algebraic function for this. So this is already in a form that's easy for me to find the derivative of. So I'm just going to find the derivative of my function, which is going to be 2/3 x, and 2/3 take away 1 is going to be negative 1/3. So what is this going to look like as a fraction? Well, it's going to be 2 over 3 x to the 1/3, or 2 over 3 to the cubed root of x. And we know the denominator can't equal 0, and the only way this would equal 0 is if x is equal to 0. So our restriction is that x can't equal 0. And so this is going to be a point where it's not differentiable. So it's not differentiable at the point 0, and if I throw 0 into here, it's also going to be 0. So 0, 0. And so what would this look like as a graph? If you wanted to see what it would look like as a graph, this is what it would look like. It's going to look something like this. And so we can see at this point, 0, 0, we have a cusp. And because we have a cusp, we know that it can't be differentiable. Part C. What happens when we have the derivative of the function, or the function, the absolute value of x minus 3? Well, let's take a look at this function. What does this function mean? Well, anytime I see an absolute value, I need to think about what is that going to be as a piecewise function. So my f at x is going to be broken up into two parts. It's going to be broken up into x minus 3, and it would be broken up into the negative of that, so negative x minus 3, or if you wanted to write that as 3 minus x, you can do that as well. Okay, so what are my points that are going to differentiate between those two? And we can think about what is it going to look like as a graph. And if I was looking at this at a graph, I would have a point here at 0, 3, and it would go up in a V. Okay, and so this 3, this x value of 3, is going to be the deciding factor between whether we're going to have the positive version or the negative version. So this is when x is greater than or equal to 3, and this is when x is less than 3. And so because we've separated that up, we want to think about now what happens to the derivative of these functions. So if I didn't have this graph to refer to, what would my derivative be? So the derivative of the first part is going to be 1. So the derivative of x is 1. And then the derivative of my constant term is 0. And then what is going to happen when what's the derivative of 3 minus x? Well, I'm going to have the derivative of 3, which is 0, and the derivative of minus x, which is minus 1. And so this is what's going to happen when x is greater than 3 and x is less than 3. Now, what happens when x is actually equal to 3? We're going to figure that out. We can see from the graph that it's not going to be differentiable at 3 because it's going to have that infinite point slope, or we can also call this as a corner slope or a corner point. So we can see from the graph that it's not going to be differentiable because it creates that corner there, or the infinite slope. And so what we can show that the limit is not going to exist as part of the derivative, to show that it also is not going to be differentiable at that point. Because I know this is what's going to happen when x is greater than 3 or less than 3, but what happens when x is actually equal to 3? Are we going to have a value there? Well, the derivative, the limit as x approaches 3 from the left-hand side of the derivative is going to be this bottom function here, which is -1. And the limit as x approaches 3 from the positive side of my derivative function is going to be +1, and the limit doesn't equal. So because these don't equal, then I know it's not going to be differentiable at that point. And that's another way that we can think about that. So it's not differentiable at the point 3, 0. So if you have a piecewise function, just to recap, split it up, or an absolute value, split it up into the piecewise functions, and then figure out what is going to be that deciding factor between whether it's going to be positive or negative. So as long as it's greater than 3, this function here will still be positive. When x is less than 3, then it's going to be negative. And then we're going to use that 3 as our critical points for the derivative function. And then we're going to see whether or not the limit exists at that 3 to determine whether it's differentiable. So if you don't have the graph, that's the way how you can do it algebraically.